Hello, everyone. Again, this is Professor Mike Hicks. I'm going to talk to you today a little bit about confidence intervals. This is the second half of week 2. And what you're seeing before you is a data extract from the American Community Survey. It's a U.S. Census product. And this is total capital expenditures of both new and used products in thousands of dollars in 2 years of 2002 and 2007. And I use this to show you how dirty data often is. The census data here suppresses small numbers of observations. So in Choctaw County, Alabama, here in this column or this row, the data are suppressed because there are not sufficient um, businesses there to deal to provide anonymity to surveyors. So they're surveyed, they're kept in the data by the census, but they're not publicly released. And some researchers can get access to them, but once they get down to the geographic level, you can't really use them well. It wouldn't be consistent with the census's legal obligation. So the first thing you have to do with all your data is understand what it is and clean it. And so in this case, we would exclude those suppressed data, which would involve, for example, sorting and removing all the D counties in this 3,144 county database of the Census of Manufacturers. And so to do that, I've just, to save time, I've done that already. So I've eliminated all the suppressed data elements for both 2002 and 2007 total capital expenditures. And then I've just measured the percentage change over that time. Those are capital investments in each of those 2 years. And so what we're going to talk about is univariate testing here. And univariate testing with confidence intervals is used most often in an environment where you have a large population, a large number of observations you want to find out something about. In this case, what's the average change in between 2002 and 2007 in the amount of capital expenditures that manufacturing firms undertook? As you can see, there's a wide variation from 170% down here to negative 31% just in this small first 10 of these observations. 800% difference, 280%, negative 70%. So there's a lot of variation in this data. Other examples that we might want to use, we might be doing quality control of medicaments. And so we know if we're selling an over-the-counter prescription medicine that the medicine itself is mixed. There's a very small amount of medicine. It's mixed in something like a caplet, which might be a benign item, mixed with flour or rice powder or chalk, that's designed to be ingested and slowly absorbed. But it would be very important to the manufacturer and the patient and the physician that every tablet have precisely the same amount of medicament in it. Well, that's just not possible, right? It's not within the manufacturing limits of the world to ensure that every tablet of Tylenol is precisely down to the 50th decimal point. Contains the same amount of Tylenol as the tablet before it. Even if it made it to the store, just traveling, bouncing around, pieces of it are going to chip off and fall away. So it's really a challenging issue. So in production process for that an over-the-counter medicament that's not very dangerous, like a Tylenol or an Advil, you'd want to sample. You couldn't test every pill, obviously, because then you couldn't send them off to your someone who might be taking the pill, right? If you tested them all, they'd never leave the factory. So you need to sample some number of the factory. And so what we want to do in a univariate test here is to see if the information we have in our sample is representative. That is one application. In the example that I have here, what I'd like to do is I'd like to randomly choose a number of counties, and I'd like someone then to survey the firms in those counties to understand why they made the changes that they did, to do a case study of it. And before I did that, what I'd want to do is to make sure that the counties that I chose were representative. And so I know now, for example, that here in this entire population, I'm going to try to figure out what the mean and standard deviation is. So I'll hit descriptive statistics. I'll choose an input range that is this full range of existing. These are going to be 12 or 1342 different counties in the United States in 2002 and 2007, and I'm going to get an output measure. I'm going to put it right here and say that's where I would like to, that's what I want to see. So the full population mean from these data are 700%, right? And the median's a 0.27, so that's dicey. And that means there's a long difference between the mean and the median. So what that probably means is the average county had about 27% increase in their capital investment. But there's some out there that were huge. They had brand new factories. Think about Elon Musk probably built something at this period of time. And we had some that the minimum was a full almost 100%. They stopped manufacturing there, and the max was 690. So this is a very large variation here. So right at the upfront, I think you're going to have to tell your boss, I don't think we can go to 30 and know for sure what's going on here. We're going to have to come up with some different strategy. But of course, you want to prepare an empirical appeal to your boss. So what I've done here is build a random number generator. You can do this easily in Excel. I've saved it as a file here for ease here. And then what I want to do to generate a sample is I'm just going to sort by this random number generator. So I go back to home, I go back to sort, and I'm going to pick the smallest 30 different manufacturing counties here to see if I could go and visit them. So I want to see their descriptive statistics because I want to compare the full known population, right, with the just let's say 30 of these. So the input range here is going to be smaller. I'm going to do the first 30 of their capital change here, so that will be 30 different, and I'm going to change their output block so I don't override it. I want to compare the two, and I'll just have it right here, and I'm going to boom. So let's see. So this is the full sample. Or the full population. Now, in the earlier example that I gave, for example, doing medical treatment, it wouldn't really be possible to do it this way because you don't know what the full population sample is. You do in the census data, you do in publicly available data, but what you might be doing in this case is your population may be earlier tests. So let's say you've been running like a medical producer or a light bulb producer might be doing. Every day we're going to draw a sample of products. We're going to measure and test 30 aspirin bottles a day, and we're going to count the tablets in each, and then we're going to sample the amount of acetaminophen that's contained in each tablet in each one of those. And I'm going to do that for the last year. So that gives me a pretty big population from which to deal with. And so what I want to do is I want to say, in that case, you have a full population number. You'll pull out perhaps a pill bottle, 30 pill bottles, do your tests on them. You come up with a different test here, and you want to see, are the means the same? Or do they contain the same average amount of medicine? In my example, what I'm doing here is different, right, than that example. What I'm doing in my sample here is I'm trying to see whether or not this random sample of 30 places that I pulled from might be giving me a reasonable approximation of the full sample in this model. And to do this, I'm going to look at the confidence interval and the mean. So I have the population, right, and I have, in this case, I have the lower bound and the higher bound. And then I also have a sample mean. That's this column 1 here. This is sample. We'll call it sample 1. And so I want to see whether or not I'm looking at the confidence interval, so I start with the mean, right? And I want to see if that minus this confidence interval is a 95% confidence interval, where that is relative to the sample. So confidence interval gives me the plus and minus from the average for both of these. And so yeah, I know from looking at this isn't going to work, right? Because the sample means a tenth of what the actual mean is, right? And so the lower bound is going to be that minus, that minus this confidence interval, and that plus this confidence interval. So it's obvious that these two don't overlap each other. We might be confident at the 95% level if they're one of their means past the other. We could do a two-way or a one-way test. And when you get to sampling for surveys, you'll get into some of the more technical details of this, how to calculate it by hand. But what's important is that this is the signal, right, and this is the noise ratio we're using. So we're looking at this. So that ain't going to work. So I'm going to have to tell my boss, I can't go to 30. I've just done a random sample of 30 different places, and I can't go to them and learn anything new. Well, he'll say, well, how many should we go to? So let's see. Let's see if again, what I've just done is I did a random number generator, and I just took the smallest, so that's a random number. It's and the places that I would be going to would be Pasco, Florida; Appling, Georgia; DeSoto, Mississippi; Bullitt, Kentucky; Walworth, Wisconsin. So a fairly reasonable cross section of places. And so let's look at another sample. Right, let's do another descriptive statistics, and this time let's go up to, in this case, 50 places. And we want to spit that information out. Oops. Right, so now we have, again, in part because we're drawing from another sample, a bigger problem. Maybe we need, so this is obviously, the mean is higher, but the confidence, as well as the confidence interval, but that's not going to get us anywhere near that level where the representative sample matters. So let's flip this. Let's sort this randomly and pick 100 from the other side. Oops. So now I'm going to do and again, these are just random places: Texas, Minnesota, Maine, Texas, Colorado, Illinois, Kentucky, Michigan. When they were originally sorted, they were in alphabetic counties within alphabetized states. So now I'm going to go back to data analysis. I'm going to go to the data analysis. I want to do descriptive statistics. I'll stick it in the same place, but I'm going to pick a top 100 places starting with the highest random number generator. And we're going to see if that works. And in reality, would you do this? Probably not, because that's a pretty... There we go. Now we can do, wow, we have a confidence interval from sample 3. Call this sample 2 now. It's really sample 3. I just didn't bother saving sample 2. Call this sample 2. Right, so we want to see if this sample here, there's the mean. Right, in this case, the same deal. There's overlap, but one would be very concerned about this random sample process. And so what I have here is demonstrating an example of using confidence intervals to make 2 points. One is the random sampling, really 3 points, if you'll excuse me. The first point is that when we're confronted with data that we sample from, that when insofar as we can learn something important about the population, we're going to be exploring a question of whether or not the summary statistics of the sample are representative of the mean. And so the practical application of this in many instances is think about survey data, think about if I'm testing medications, if I'm asking public opinion on elections, that's survey data. I'd want a representative sample. So I would go out of my way to try to pick a sample that looked like the population. And what matters is the question you're asking. So the question you're asking in a public opinion survey would be, let's say it's election time, you'd like candidate X or candidate Y. And so you don't know what people want. You don't know what the population's interested in. But what you can do is select a representative number of respondents whose characteristics represent this population as a whole. So in that case, you're going to want 51% women, 49% men, you want 32% Republicans, you want 29% Democrats, those are registered voter applications, you want 14% African Americans, you want 12% Hispanic whites, you want 7% Asians, you want the remainder white. You want to have a population that looks like the question that you're asking. And in the second example, so that's the first thing, that the research question that you're asking is going to drive the population parameters that you're looking at. The second point that I'm making is that the larger the sample size gets, the more likely it is to be representative of the population that you have. That's why we talk about a central limit theorem. Sort of 30 observations allows us to do some statistics here, and the variation's so high that 30 observations, even 100 observations randomly drawn from this population is not going to work. Particularly because what we're looking for here is the variability of capital investment within a county in terms of percentage change, and that's going to be driven by a wide variety of potential outcomes. And then the third point that I wanted to make is that there's a mechanism for comparing means, in this confidence interval. This is actually is a version of a z-statistic. All types of statistical tools measure the signal, in this case, which is the average, that's the signal, and then the noise, which is the distribution. In this case, the distribution around this, which we're hoping is random. It isn't necessarily, but we're hoping it's random and normally distributed. And so, those are the 3 major points. On top of this, what we also find, and I find as an active researcher, is that many times the sampling process doesn't give us a very clear guidance by itself. So if it were, much of what could be solved by the world could be solved by a big data analysis with no thinker attached to it. And I mean, a lot of people thought that big data would give us this answer, but really theory has to drive this. So what we might do here is compare the composition of manufacturing in each of these counties, and then we might randomly choose those that had high share of automobile or transportation equipment. Those were high in consumer non-durables such as clothing and food, because those types of firms have very different types of processes. So maybe just the amount of capital investment they made isn't the variable we're interested in. Maybe what we're really interested in is why do different firms do what they do. And as you move through your MBA process and you think more about different elements of what you're trying to learn, that's going to be driving what you do as much as, and particularly in the early phases, as building a hypothesis. And so what we'll do next week is we'll start going through some hypothesis tests. We'll move quickly away from univariate analysis because the hypothesis there is about the sample in itself. And what I want to teach you over the next 2 or 3 weeks is how to compare two different groups of populations to see what they tell, or two different characteristics about a simple population to tell us what they say about that population and whether or not there's any useful inference from that. So this really ends our quick lecture, a couple of weeks on summary statistics, on central limit theorem, a quick review of sampling and confidence intervals in a univariate or single variable setting. We're going to move now to multivariate or multivariable, so we'll be comparing two or more different things as we go along. So have a good weekend, and I'll see you electronically next week.